All right, welcome. Today, we're going to pull off a little digital heist. We're going to find a program's hidden rules, and then we're going to break them. This is a classic hacking technique, and it gets right to the very heart of how software really thinks. So, to kick things off, let me just ask you a simple question. Okay, so picture this. You're playing a game, it's the final move. Everything's on the line. And what if, right then, you could just secretly rewrite the rulebook to make sure you win? I mean, that sounds a lot like cheating, doesn't it? Well, in the world of software, that's not just possible, it's a very real and very fundamental type of hack that takes advantage of how a program is designed to think. Now, every good heist needs a target, right? And ours, it's something really specific and really powerful, buried deep inside a program's memory. We're going after what's called a function pointer. Think of it as the key that can unlock the whole system if we just know how to turn it. So, what is this thing really? Well, unlike a regular variable that might hold, a number or some text, a function pointer holds an address. And not just any address, it holds the address of a chunk of code, a function. It's kind of like the program's director, pointing and saying, okay, when I give the signal, I want you to run the code that lives right over there.
The easiest way to get your head around this is to think of a speed dial button, maybe on an old school phone. You press the number 1 and boom, it instantly calls your best friend. Now that button doesn't contain your friend, right? It just holds the number it's supposed to dial. A function pointer is exactly like that. It's just a shortcut, programmed to run one very specific piece of code.
And that is where our plan really starts to take shape. Because what if? What if we could sneak in and change the number that's programmed into that speed dial button? So instead of calling your friend, all of a sudden it's calling, well, anyone we want it to call. That's precisely what we're about to do. Okay, to show you how this works, we're not going to be breaking into a massive bank vault. No. We're going after a much simpler target, a little C program from our source material called Game of Chance. It's going to be our model system, perfect for a bit of, well, let's call it reconnaissance. Yeah, on the surface, it just looks like a simple little game. But just like any well-designed vault, it's got a specific structure. And that means it has specific weaknesses. You just have to know where to look. So come on, let's pop the hood and take a look at the blueprints. And here we go. These are the blueprints. This gives us all the clues we need. So first, we've confirmed our target. There's that function pointer, and look where it is, stored right next to other user data. But here's the kicker. A key variable isn't properly set up from the start. What that means is the program just sticks it in this special, super predictable spot in memory. And that makes it a perfect stationary target for our attack. Okay, so with our intel gathered, we've found the flaw. The program has a vulnerability, a crack in its defenses that we can absolutely exploit. It is a classic mistake, and it's called a buffer overflow. So let's break down the plan. So what's the crucial weakness here? It really all comes down to trust. The program asks the user for some information, let's say your name, and it sets aside a little box in memory to hold it. But here's the problem. It just blindly trusts that you won't give it a name that's too long to fit in that box. And that trust, well, that's going to be its downfall. I want you to think of the computer's memory like a row of mailboxes, all lined up. The program says, okay, here you go, mailbox number 1 is for your name. But what happens if you send a letter that is so ridiculously huge that it doesn't just fill your mailbox, it spills over and starts cramming itself into mailbox number 2 right next door? That is a buffer overflow. You are literally writing data way outside of its designated space. And this right here, this shows you the result perfectly. Look, on the left, everything is normal. The user's data is sitting nicely in its spot, and our function pointer, our speed dial button, is right next to it, pointing to the real, legitimate game function. But then look at the right. After we send way too much data, it spills over and completely overwrites that function pointer. Bam! We've just reprogrammed the speed dial. So here it is, the final plan, all broken down. It's a beautiful, elegant 5-step process. Step 1, we send that oversized input. 2, the extra data spills over in memory. 3, that overflow overwrites the function pointer right next to it. 4, the pointer now points to our new malicious function. And then step 5, we just wait. The second the program tries to use its speed dial, it's not calling the game anymore. It's calling us. Heist complete. Okay, so we did it. We successfully hacked a simple game. And I know what you might be thinking. That's a neat trick for some old program, but what about today? Does this stuff still matter? Well, let me tell you. The principle behind this exploit is just as relevant now as it ever was, maybe even more so. And I am not exaggerating here. This exact class of vulnerability, overflowing a buffer to hijack a program's flow, is responsible for some of the most infamous, most damaging hacks in history. We're talking billions in damages. It's a truly fundamental flaw in how we as developers handle memory. You see, the core idea is pretty much universal. It's especially powerful in languages like C, which basically give developers the keys to the kingdom, raw power over memory, but with no automatic safety checks. Yeah, a lot of modern languages have built-in safety nets to try and prevent this, but the underlying principle is still there. Find where a program stores a go-to instruction and figure out how to overwrite it. This technique, in all its different forms, has been used to attack pretty much everything that runs code, from web servers to entire operating systems. And that really leaves us with one last kind of nagging thought. Sure, modern software has way more protections, but it's also infinitely more complex. So as you go about your day, using all the dozens of apps and systems on your phone and computer, it's really worth asking yourself how many of those games that we all rely on are still built on a foundation that just trusts you to put the right amount of letters in the mailbox.